Hello, I am Eric Andrews. I am currently a student at the University of Idaho working on a Master's of Engineering in Electrical and Computer Engineering. I am going to be giving a talk today on short wavelength imaging technologies and their uses. Since I am recording this instead of being able to present this on site, you can email me any questions that you might have at my email address that I have listed on the screen. I'd be happy to answer any questions that you might have. Today I'm going to give a quick introduction and some background on the shortwave imaging, where we want to take a look at it, and kind of go into some of the light spectrum and photo imaging background there, so that we have a basis of where we're going. I then want to go in and take a look at some of the applications that we have for UV imaging, what some of the uses for UV imaging is out in the industry and why we care about it. Pixel technologies, these are primarily the electronics behind the UV imaging. How do we create a pixel that is going to be sensitive in the UV area of the spectrum, and then some processing improvements that we can use for these UV imagers in order to ensure that we get the light captured efficiently and quickly. Finally, we're going to go into a conclusion and hopefully wrap everything up. So jumping into the electromagnetic spectrum and our introduction. The electromagnetic spectrum is made up of different wavelengths of light. The primary one that we think about is visible light in the 400 to 780 nanometer range. Above 780 nanometers you have infrared, and below you have the short wavelengths, ultraviolet, X-rays, gamma rays, and we have different uses and reasons for capturing and caring about light here. The ultraviolet is also broken up into different sections: UVA, UVB, UVC, and vacuum UV. These are just different wavelengths that have different responses on different materials and can provide different bits of information that may be useful for the experts taking a look at this data. In semiconductor imaging, as we should know from the class, it was initially pioneered in the 1960s and advanced fairly rapidly from there. There's a variety of technologies possible: CCD pixels, CMOS pixels, using photogates and photodiodes, and a variety of photodiodes. When we're taking a look at semiconductor imaging for UV imaging, some things to consider are, will the material transmit UV light? Since we can't see it, we need to pay attention to this to make sure that we're not missing something or accidentally filtering out this light when we're trying to capture it. Where will the photon be absorbed in the photodetector? I'll get more into this later, but it's important to know this since silicon primarily is near the surface. We need to make sure that we're setting up the detector so that it will capture the photons and convert them into electrons so that we can process the data. And then we also need to worry about, since these are shorter wavelengths, they have higher energy, we need to consider protecting the circuitry from higher energy particles, particularly X-rays and gamma rays, but even some UV protection is going to be necessary if it's the right type of UV radiation. So going into applications of UV imaging, there's a lot of different uses from industrial, medical, criminology, research, and others. In industrial, it's used for non-destructive testing, inspection, leak detection, even windshield repair can be done. You can see on the slide an example where the left-hand side you've got a CD that has been imaged with visible light, and on the right-hand side it's been imaged with UV light, and you can really see the scratches come out. Just an example of where it can be used there. In medical, it can be used for dermatology, DNA testing, E. coli testing, even going into X-ray imaging, even though that's I don't spend a lot of time focusing on X-ray. It's still an area that we want to pay attention to when we're taking a look at these imagers and possibly optimize for, as it has tremendous use in this area for medical. Criminology, they can go to crime scenes and get just to help illuminate some evidence in other ways due to the interactions with the UV light. They can use it for counterfeit detection, arson, toxicology reports, things of that nature. So it's very useful there as well. In research, they can do mycology. Of course, if you're familiar at all with NASA and Hubble, you've probably seen some UV or X-ray or deep space images, mercury detectors, mineralogy, others you can get into just hobby photography or cinematography if there's a specific use that they have in mind in order to bring out something a little bit different. It can be done there. These are just a couple of the different options for applications and why we want to continue to push optics and particularly semiconductor optics in this area. So going into pixel technology now. In general, silicon has pretty poor responsivity to UV light and therefore low low gain, but silicon isn't the only option that we have for semiconductor technology. In the lower left hand side, I've got different options there. UV silicon, silicon carbide is an option there, which can help to increase UV sensitivity. The other options here, indium gallium arsenide, germanium, are other very commonly used ones, though they go in the wrong direction for UV light and can be used more for infrared sources. For UV light, we generally want to take a look at 3-5 semiconductors or semiconductors that have a wide band gap. These are going to be able to be used in order to capture the light that's coming in the higher energy particles and be able to capture them more efficiently. Gallium nitride is one that's used fairly often in UV light. Some possible downsides of switching to some of these other options is it can make processing more difficult. They might be a little bit harder to tune. And even with gallium nitride or the aluminum gallium nitride Schottky diodes, you can change the doping characteristics of that and get it to respond to different wavelengths there as well. But this has the downsides that you've got to be more precise in your processing in order to get the response that you want. Also, you're going to be restricting the wavelength range on a lot of these responses. As you can see in the top right hand graph, as you're going to some of these gallium nitride imagers, they're very, very poor in visible light, so they're not going to be useful for anything beyond the UV spectrum of light. But they are options that we can do in order to get better imaging and better response in those areas. The other thing to consider is skin depth. Where are we capturing it? For most of these semiconductors, we're still fairly shallow in the UV light, similar to what silicon has. So we need to make sure that we've got a depletion region near the surface of the semiconductor so we can capture the photons efficiently. The common ones here are PIN photodiodes and photogates that have a depletion region very near the surface. Another option is to use Schottky photodiode. In Schottky photodiodes, you have your a Schottky diode is essentially a diode made up of a metal barrier with a semiconductor. Where this is useful for UV light is the metal, when selected properly, will penetrate through the metal layer and be able to be collected very near the semiconductor surface. So you can bias it in such a way that you have your depletion region in the semiconductor right there at the surface, and you don't have to worry as much about some of the other effects and other noises that we get with traditional photodiodes. However, Schottky diodes are also somewhat have a higher leakage current when reverse biased, so you might have more noise associated with that. And there's also difficulties in processing Schottky diodes, particularly when it comes to photodiodes. There's been some anomalous behaviors identified in the electronic circuitry of these Schottky photodiodes. So you need to make sure that your process is well dialed in order to prevent a lot of noise in a pixel array and help you to be able to get it. The benefit is that you're able to get that near surface collection on the semiconductor, and you're able to integrate it into a CMOS technology, so you can use a lot of the same readout circuitry that we had for CMOS image sensors. Moving on to processing improvements, there are back illuminated sensors instead of the traditional front side illuminated sensors. This is an extra processing step that can be done. Basically what you do is you take your grown photodiode and circuitry, you put another silicon wafer on the front, you flip it over, and then you grind the backside down so that you've got a very shallow surface. You're basically taking off all the substrate layer so you can get down to the epitaxial layer, and then you have your photodiode that is biased in such a way that you have a depletion region very close or right to the surface there after you're done back grinding. And then you add a passivation layer or have a negative charge right there on the surface in order to prevent electron traps, because you are going to be producing a lot of electron traps in the grinding process. And then you can add your anti-reflective coating on top of that. So you can get more direct light to the photosensitive area of your photodiode with the back illumination, which is very important for UV light. You're not going to have as much reflection and get a lot more direct light there. But you've got additional processing steps, and then you've also got the passivation layer and electron traps that you're going to have to pay attention to. Other options that you have for UV light, you have materials called scintillators. Essentially, this is fluorescence material. This is material that, when hit by UV or a high energy particle, it'll actually absorb that high energy photon and release a lower energy photon. That way you can basically convert these high energy UV, X-ray, gamma rays into a visible light or a lower energy that can be collected more efficiently with existing image sensor technology. It also has the benefit of being able to put over the entire surface or in front of the entire imager and protect all of the circuitry. Particularly when you're into the X-ray and gamma rays, you're going to be having a lot of high energy photons that are going to be causing a lot of damage, and this is one way that you can do it. However, one common scintillator is sodium iodide doped with thallium, which produces a peak wavelength of 415 nanometers, and it will produce approximately 38 photons per kilo electron volt gamma ray, and has a 250 nanosecond relaxation time. Basically, when you get your image sensed, you're going to have to wait so long before the previous one is gone. So if you're going and you've got a very wide range of light that you're trying to capture in quick succession, it's going to slow down the frame rate that you can have there. So you're really not going to be using this for a moving image and for high speed, but it will be effective in that. Also, if you've got other types of scintillators that may be higher efficiency, they may need some special handling in order to make sure that they're not exposed to air or water or things like that, or they'll break down and they'll lose their fluorescence qualities. Other things that you can do are use improved UV filters. Most of the filters that you take a look at are optimized for the visible spectrum, since that is primarily what we as humans care about. By switching to a UV filter or others, you can filter down to the UV spectrum that you care about, so that way we can make sure that we've got that. One other thing to note is a common passivation layer used is silicon nitride. This tends to be a high reflector of UV light. So there's been work going on in order to make sure that silicon nitride can be able to transmit more UV light and be able to collect more of those photons, so that we can get that image a little bit more accurately and better. But this is still ongoing research. I saw research online stating in 2011 that they've got some advanced, but it's still going to be fairly new technology, so it may be more expensive in that way. In conclusion, UV light provides several areas of challenge for pixel imagers. In UV and X-ray and gamma light, with short wavelengths, in order to make sure that we can capture the image. Using gallium nitride or other semiconductor materials can help improve UV response, though if you've got a near UV light, something in the 300 to 400 nanometer range, you can still use a traditional silicon photodetector. Pin photodiodes, photogates, and Schottky diodes are often utilized in UV sensors and short wavelength sensors in order to capture that light near the surface. And then back illumination, scintillators, and UV filters are processing steps that we can use to capture the light in different ways. So that concludes my talk. Thank you for your attention. Again, if you have any questions, you can direct them to my email address. It is andr9408@vandals.uidaho.edu. Thank you.